When dealing with engineering and architecture, one of the values we contemplate most deeply is likely efficiency. This is because we want to get the best possible performance and use of space out of the given constraints. However, the building we're looking at today, Sendai Mediatheque, completely flips the script. Even with a massive budget of 13 billion yen, its full glass facade makes it notoriously difficult to heat and cool, and it even suffers from several internal noise issues, making it inefficient. Yet, despite these flaws, the world hails this building as a masterpiece of modern architecture. Today, we plan to dissect this contradictory building, designed by Toyo Ito, entirely from a perspective of architecture engineering students. Here is an overview of the story we will explore today. First, we will examine the design philosophy and background. The core concept this building sought to protect, even at the cost of extreme inefficiency. Second, we will talk about the structure and construction process that turned this unconventional, column-free and wall-free design into reality even under conditions with high risk of earthquake. Third, we will analyze the facade mechanism that completes the building's sense of openness. Fourth, we will propose our team's unique facade improvement plan to compensate for the thermal and acoustic drawbacks mentioned earlier. Finally, we will summarize the architectural lessons that we learned from this inefficient masterpiece.
Double facade. Tube structure. Sendai, Japan. 7 stories. A cultural complex, the Sendai Mediatheque.
In the early 1990s, the city of Sendai planned a new public facility to integrate several services that were scattered across the city center. This single hub would house the city library, community gallery, an audiovisual learning center, and an information center for the visually impaired. But Sendai didn't just want a standard community complex. They envisioned a radically new kind of public space where books, art, and digital media would seamlessly merge. An open hub where citizens could unlock their potential and connect with one another. That is why it is called Mediatheque. To achieve this, an open competition was launched in 1994 with clear judging criteria. It had to create a space that was open to the entire city, and it had to pioneer an original piece capable of responding to a new era. And as a result, Toyo Ito's design proposal was selected. Typically in architecture, function is determined first, and rooms are divided according to that function. These closed rooms then come together to form a single building. However, the Sendai Mediatheque reverses this sequence. Rather than being in a box that confines function, it redefines the building as an open field where flows and events take place. Instead of closing off spaces with walls, the structural tubes create a seamless flow, connecting people and the atmosphere. It is as if the city streets and the building have become one. The core element that translates Toyo Ito's design philosophy into a physical building is the tube. Going beyond a mere structure that supports the building's load, this tube dismantled the traditional concept of closed, confined rooms and served as a key mechanism for creating a natural flow within the space. To implement an innovative design philosophy required a massive budget. Moreover, since Japan was going through the so-called lost decade right after the collapse of the bubble economy, there was a backlash from citizens and the media. Even under intense criticism, the project moved forward, all thanks to the 3 key turning points in persuasion. Firstly, it had the fierce backing of Arata Isozaki, the head of the judging panel. During the competition, he publicly declared, "The winning proposal will be the one that breaks the mold of conventional architecture." And once upon seeing Toyo Ito's design, he personally persuaded the city's authorities, stating, "This design will place Sendai at the very center of the architectural world." Secondly, was because of Mayor Fuji's vision. At a time when the internet was expanding exponentially, his goal was to elevate Sendai beyond its status as a provisional city, turning it into a pioneering hub for the new information society. He judged that the building would create the branding effect, ultimately outweigh the immense costs in the long run. Lastly was through endless communication with citizens. Over a period of more than 5 years, Toyo Ito and the city of Sendai conducted countless workshops with the citizens. A space where a library, gallery, and media center blend seamlessly without walls. A structure that achieves a completely open, column-free plan using just 13 hollow tubes. An approach where the architect builds the frame and the citizens fill it with life. By leaning heavily on these three concepts, they were finally able to win over the critics and shift public opinion. While they had successfully persuaded the public, the real challenge lay ahead. This was because Sendai is an area with an exceptionally high risk of earthquakes, even within Japan. This is an actual footage filmed inside the building during the 2011 earthquake. So how was Sendai Mediatheque able to withstand such an earthquake solely relying on the tubes? Starting from the basement, let's explore the secret that preserved both the structure and the architectural philosophy of the building. This site is close to the Hirose River, featuring high groundwater level and highly permeable sandy soil. Because deep excavation poses a significant risk of soil collapse and massive groundwater influx, the slurry wall method was adopted. The first step of construction is installing the guide walls. Subsequently, rather than excavating a large area all at once, the construction is carried out in sections on a panel-by-panel basis. And by completing the primary panels first, allows the soil between them to naturally act as a support, thereby preventing collapse. Each panel is constructed through 4 stages. First, a machine called grab excavator digs down to the designed depth. Once the excavation is finished, a large crane lowers a steel reinforcement cage into the trench. Finally, a tremie pipe is lowered to the bottom, and concrete is poured from the bottom up. Once the initial excavation is complete, stop bands are inserted vertically at both ends of the panel. Now the excavated space is filled with concrete. Next is the secondary excavation. In this stage, the soil remaining between the primary panels is excavated. Finally, by filling the remaining space with concrete, the separately constructed panels are joined together to form a single, integrated wall. With this, the underground structure supporting the Sendai Mediatheque is completed. After stabilizing the ground with slurry wall, the entire area for the underground structure is excavated. Once the excavation is finished, concrete is poured to create the foundation slab, and a crane is installed on top of it. On this foundation slab, the columns for the second basement level are constructed. As you can see, these are hollow, cylindrical concrete structures, and this column serves as the legs that support the tube structures above. Now, it is time to construct the columns for the first basement level. These columns must strongly resist not only the compressive forces from the building's self-weight and the horizontal lateral forces during an earthquake, but also the uplift forces that act to lift the building. Therefore, a highly robust connection method is required. First, a 2050mm long steel pipe pile is inserted deeply into the cylindrical concrete structure of the second basement level to ensure the structural integration of the foundation and the column. The column is then precisely seated on top of the steel pipe. At the top of the column, a collapsible beam is installed. In the event of strong earthquake, this beam is the first to break, absorbing the energy to protect the primary structure. Once the earthquake has passed, the building can be restored to its original performance simply by replacing the damaged beam. Finally, concrete is poured on the first basement floor and the first floor. Between the underground exterior wall and the first floor, a roller bearing system is installed. The roller bearing is a device that isolates the building's movement from the ground, which dramatically reduces the impact of an earthquake. and it reduces seismic acceleration by up to 10 times compared to a fixed ground structure. The foundation is now complete. Now let's move up to the ground level. The core structural elements of Sendai Mediatheque are the tubes and slabs. They are all prefabricated in a factory and then assembled on site. This approach ensured the precision of irregular members and shortened the construction period. However, no matter how precisely they are manufactured, they are exposed to risks such as bulking, lateral displacement, and torsion during assembly. Therefore, secondary steel frames are installed inside the empty space of the tubes during the building's assembly process. The secondary steel frames serve two purposes. First, it acts as a column to prevent lateral displacement and torsion until the tube is completed. Second, it acts as a jig to prevent deformation caused by welding heat and to fix the members precisely at their design coordinates. Once the underground construction is finished, a crane lifts the first floor tube and sets it on the slab. Because the tube is unstable on its own, a secondary steel frame is immediately installed inside it. The second floor tube is then hoisted on top of it in the same manner using a crane. Horizontal beams are installed to the disc section where the first and second floor tubes meet, connecting the tubes to a secondary steel frame. This secures the exact position of the tubes and prevents swaying and torsion. Once the tubes are set in place, it is time to install the slab. Because the slab is very heavy, it cannot support its own load until it's completely welded to the tubes. Therefore, temporary support known as system shoring are installed to hold up the slab. Once the shoring is installed, the lower steel plate of the slab is assembled on top of it. Next, the internal framework of the slab is arranged over it, and finally, the upper steel plate is placed to complete the slab for that floor. This concludes the construction process for a single floor.
Now let's look at it at a wider point of view.
The first floor tube, secondary steel frame, and the second floor tube are erected on top. System shoring is then installed to support the second floor slab. Here lies the first key principle. The shoring is dismantled only after the slab is completely welded to the tubes and becomes structurally self-sufficient. After repeating this process up to the top floor, the second key principle comes into play. An external crane is used to dismantle the central tower crane as well as the secondary steel frame inside the tubes. And the moment these secondary steel frames are removed, the iconic tube interior of the Sendai Mediatheque as we know it is finally revealed. Now, let's examine the structure of the slab. In a typical building, beams are installed between columns to support the slab. However, because the columns in this building are in the form of tubes, conventional beams cannot be connected to them. Therefore, the slab itself had to have sufficient flexible strength. To achieve this, a 400mm thick steel sandwich structure was adopted. Stiffeners called ribs are arranged in a grid pattern between the upper and lower steel plates to form a framework highly resistant to bending. And lightweight concrete is poured on top of this. Then, how are the forces from the slab transferred to the tubes? The slab is divided into three areas based on the load transfer mechanism. The first is Area 3, the general zone. Here, beams with a rectangular cross-section are arranged. The load applied to the slab flows axially along these rectangular beams and is guided into Area 2. Next, in Area 2, the zone where the tubes are linearly arranged. In this area, the beams are arranged in square grid pattern to align the load parallelly. The load entering from Area 3 changes direction along the x-axis and is evenly distributed towards its final destination, Area 1. Area 1, also known as the disk zone, connects directly to the tubes. In this area, the structurally complex radial redistribution occurs to completely transfer the load to the tubes. Elaborately arranged triangular steel beams receive this load and transfer it directly to the ring-shaped I-ring beam connected to the tube. In this way, the load is transferred to the tubes without the use of solid walls and create an open space. Now, how is this open space connected to the exterior? The Sendai Mediatheque employs a different type of glass facade for each side of the building.
Let's now examine the double-skin facade on the south side. The base of the facade remains permanently open, allowing outside air to enter the cavity between two glass layers. At the top, an adjustable air gate controls whether this air is retained or released. In winter, the upper gate is closed so the air heated by sunlight remains inside the cavity. This warm air layer works as a thermal buffer, reducing heat loss from the interior. In summer, the upper gate is open. As the cavity air is heated by solar radiation, it rises through natural convection and exits through the top. At the same time, cooler outside air is drawn from below, creating continuous airflow. This removes solar heat before it is transferred indoors, reducing the cooling load. Structurally, this facade is not supported like typical frame curtain wall. Instead, it uses a metal point glazing system. Hanging rods act as the main supporting members, and brackets and bolts connected to these rods hold the glass at selected points. The load of the glass is transferred through these points connected to the hanging rods, then to the building structure. Because visible framing is minimized, the facade appears highly transparent, almost as if the glass is floating in the air.
Sendai Mediatheque carried two major environmental problems for its actual users. First, it suffered from high heating and cooling load, as well as indoor comfort issues. Second, it faced a noise problem caused by the busy main road and poor acoustic insulation. In response, we thought of an alternative plan to remodel the glass enveloping the building using high-performance materials. We have selected two key materials, double silver low-E insulated glass filled with argon gas, and PVV laminated glass. These materials effectively block solar heat gain while preserving the building's signature transparency and enhances acoustic insulation performance. While maintaining the existing system for the double-skin facade, on the south side, we proposed two scenarios for replacing the exterior glass walls on the north, south, east, and west elevations. Plan 1 applies the combination of low-E glass and laminated glass to the south and west side, which receive high solar radiation, and applying standard laminated glass only to the north and east side, where sunlight is relatively limited. Plan 2, by contrast, applies the combination of low-E glass and laminated glass across all four sides. So how does this two plan compare in terms of energy savings and economic feasibility? To calculate the construction cost estimation, we factored in only materials, factory fabrication, transportation, and on-site installation. Based on this calculation, the total construction cost is estimated at approximately 343 million yen for Plan 1 and approximately 408 million yen in Plan 2. Next is the energy consumption reduction. According to the simulation results, both plans significantly reduce the winter heating load in terms of energy consumption. However, it triggered a greenhouse effect. Consequently, the cooling energy savings during summer were relatively marginal. For Plan 2, the results were actually less favorable in terms of cooling performance compared to Plan 1. Using the reduced energy consumption levels, we calculated the financial savings. First, let's examine the electricity rates. This analysis applied the 2026 high-voltage commercial electricity rate. As a result, the annual electricity cost savings from Plan 1 is approximately 3.49 million yen and approximately 2.71 million yen for Plan 2. And for heating load, it is converted using city gas rates. It is calculated by applying the standard heating value of Sendai City Gas 13A and Sendai City Gas 2026 commercial contract unit rate for heating. The annual gas cost savings are projected to approximately 3.25 million yen for Plan 1 and approximately 4.43 million yen for Plan 2. In conclusion, we can expect annual energy cost savings of approximately 6.7 million yen for Plan 1 and approximately 7.14 million yen for Plan 2. Looking at the payback period relative to construction costs, it takes 51 years for Plan 1 and 58 years for Plan 2. However, these figures are simple calculation based solely on reduction of HVAC loads. The remodeling of project must be evaluated not only through energy cost savings, but also through the long-term value improvement of public architecture. When comparing the two options, Plan 1 emerges as the most realistic and viable choice. Finally, let's look at the solution to the noise problem. External sound is effectively mitigated by the PVV laminated glass on the facade. By combining two distinct glass thickness, 6 and 8 mm, we disrupt acoustic resonance. Through this approach, we can significantly elevate the sound insulation performance from the baseline STC34 to an optimal range of STC39 to 41. To address the internal reverberation caused by sound reflecting off the tube glass, we plan to apply transparent acrylic micro-perforated panels. Through this application, the indoor reverberation time, which previously reached a maximum of 2.8 seconds, is significantly reduced to an optimal range of 1 to 1.6 seconds. This material effectively controls indoor noise without compromising the transparency and openness. As we've seen, the Sendai Mediatheque is an inefficient building, yet these compromises were necessary to achieve the building's core architecture mandate, the absolute elimination of walls. When we envision architecture, we instinctively think of walls, columns, rooms, and ceilings. But by eliminating the wall, Sendai Mediatheque offered the world an entirely new structural paradigm. This radical innovation didn't stop at the design phase. The construction process demanded the exact same level of creativity. To connect the concrete slabs with the irregular twisting steel tubes, the builders borrowed techniques from traditional concrete construction. Because the site was incredibly tight, they had to erect the tower crane by piercing it straight through the center of the floor plates. Furthermore, the dismantling of the temporary shoring frames strategically utilized the hollow geometry of the structural tubes. Ultimately, the project succeeded not by inventing entirely new technologies, but by repurposing existing familiar systems to fit a highly unique architectural context. And that brings us to a very first lesson of this project. Creativity does not belong solely to the architect. However, not all these creative ideas were a complete success. As we've seen, stripping away the wall created massive acoustic challenges, and that beautiful fully glazed facade made climate control a nightmare. And here lies our second core lesson. Architecture is inherently a continuous series of trade-offs. It is a deliberate process of deciding what to prioritize and what to compromise, and each of these engineering decisions carries an ongoing responsibility. So then why do we call this inefficient building burdened with so many flaws and masterpiece? If we justify Sendai's inefficiency simply because it's a public building, then in the private sector, where profit is king, everyone should be just building cheap, rectangular boxes. But we know that that's not the reality. Apple Park is beautifully inefficient, so is the Tiffany flagship in Ginza. Whether we call it public identity in the civic sector or branding in the private market, creating iconic, game-changing space isn't a luxury reserved only for public architecture. In the end, the Sendai Mediatheque isn't perfect, but wrapped inside all of its flaws were deliberate intention and bold choices, all made to give people a completely new way to experience space. There's no single right answer in design. You can change your materials, adjust your budget, but you will never satisfy everyone. What really matters is looking at all those pieces and having the courage to make a definite choice. Through this project, we have learned that architecture isn't about finding flawless blueprints. It's about deciding what is worth fighting to preserve and what we are willing to compromise.